Welcome to this lecture of mechanical vibration. In this lecture we are going to cover single degree of freedom force vibration of a damped system. In my last class I have covered the force vibration of an undamped system, but here we are considering the damping and we will try to get the response of a damped system. So here I am showing one basic mathematical model of a mass, spring and damper, and here I am applying a harmonic force of angular frequency omega and the magnitude f naught. So when I will apply this force on this system, there will be vibration of this mass, and if I will make the free body diagram of this mass, assuming that the mass at this instant, the mass is moving in the downward direction with acceleration x double dot, velocity x dot, and displacement of mass from its mean position at this instant is x. So this is my free body diagram where the force is acting in the downward direction, but the damping force as well as the spring force is acting in the upward direction. So when I will apply the D'Alembert principle, I know that in case of D'Alembert principle, the forces acting in the direction of the acceleration will be positive and other force will be negative. So after doing the force balance, I will get this expression. This is the governing equation for a damped system under the excitation of harmonic force. Now I have to get the solution of this non-homogeneous ordinary differential equation. This is basically a non-homogeneous second order ordinary differential equation, and in mathematics we have a standard procedure to get the solution of such equation, and that includes two parts. One is the homogeneous solution, another one is the particular integral solution. So this is PI part and this is homogeneous part. And how you get this PI part and homogeneous part? When you want to solve the homogeneous part, you ignore the term here and consider it 0. That means basically, if you will recall our damped free vibration, where our equation was like mx double dot plus cx dot plus kx is equal to 0. So homogeneous part is nothing but the case where you have the free vibration. When you do the particular integral part, in particular integral part you have to assume one solution, and in this case you know that your force is harmonic, so your response will also be harmonic. So you will assume one harmonic function as a response and you will put back your harmonic function here and you will get the particular integral part. These things are fairly available in many books, so here I am not going to give the complete derivation. I will going to focus that what is the physical significance, what are the interpretation, what are the important interpretations which is useful to solve the numerical as well as for having a physical essence of the damped force vibration. So now, as I said, that for the homogeneous part I am going to ignore this part, and that will be the standard solution of a damped free system, and this is the solution of a damped free system. If you are interested, you can see my previous video of damped free vibration where I have derived this equation where A and B are the constant and can be calculated by initial displacement and initial velocity condition. For a particular integral part, as I said, that I have to assume one harmonic solution, and you can see that I have assumed the harmonic solution x cos omega t minus phi. If you recall the free force vibration of undamped system, there I have considered the cos omega t, where here I have included one phi. And why I have included this phi? Because I know that when there is a damping, the force and the displacement will not be in the same phase. If we are having a damping, the phase of the force and the phase of the response of the mass, that means the motion of the mass and the motion of the force will not be in the same phase. How you can define that? It means that suppose force is varying from a value of minus 10 to plus 10. So when the force will be at its maximum position, your displacement will not be at the maximum position at that instant. The response will reach to its maximum position at some other time. That means both are not reaching at the maximum and minimum value at the same time, therefore they are not in the same phase, they are having a different phase. And what would be the phase difference? The phase difference here defined by the phi term. So this is the most general form to consider for particular integral. Even for a undamped system you can consider this, but we know that there both will be in the same phase, so we ignore that part. Now as I want to solve the particular part, what I will do, I will put this value into the general equation, and here is the expression. When I will put this xp here, first I will double differentiate this, so I will get that minus omega square x, this cos term. When I will put back all the values here, I need the velocity. My velocity will be what? My velocity will be omega x sine omega t minus phi. So when I will put these three values in this equation, this is my expression here, and in this expression what I will do now, I know that cos a minus b formula, I know sin a minus b formula, so I am going to open this term, and after opening this term, what I will do, I will equal the cos coefficient from the right hand side and the left hand side. When I will equalize the cos and sine coefficient, here is no sine coefficient, so whatever sine term will be here, that will become 0, and whatever cos components are here, that will become equal to f naught. So finally I will get this expression. This is the trigonometry formula, and after equalizing these two terms and solving the equation, I am not solving here, it is available in many books, so you can see, because I am interested to give you the final result, and when I will solve it, I will get two values. One value will be depend x and another will be phi. So I am getting these two formula. For x I am getting this expression, where f naught is the magnitude of your force, which I have already defined here, and the km is the stiffness and mass, omega is the excitation frequency, c is the damping. Similarly, I will get the expression for the phi term, that is tan inverse c omega k minus m omega square. Now I can further modify this term, and how I can modify this term, I know that my damping is c by cc, I know that omega natural square can be written as k by m, and I am defining one term r, which is the ratio of the excitation frequency and the natural frequency. When I will put all these terms in my previous equation, I am getting this expression. This you can remember this expression. If you are not able to recall all other things, these two formulae are very important, and you should remember these two formula for a damped force vibration case. So this is known as your magnification factor. When what you will do, this is your static deformation, so you can write that x by del static, that would be what, 1 by under root 1 minus r square whole square plus 2 zeta r whole square. I know that this is bit more mathematical, but there is no other choice. We have to see this part, and what are the important thing, I will let you time by time. So for the damped force vibration, these two formula are important. Not only for your engineering examination, it is also important for many competitive exams. You can see one question every year in the GATE examination based on either these two formula. So now if this is my magnification factor, and I am interested to see the variation of this magnification factor with respect to the r or zeta, so what I do, I will consider different value of zeta, and I will plot my system. Suppose my zeta is initially 0.1. So now zeta is fixed, and I will vary my r. How I will vary my r? Mathematically I am saying that I am going to vary my r, but physically what I am going to do, I am going to change the excitation frequency, because natural frequency is constant for a given system. So I am going to change the excitation frequency, and I will see what happens to my system. Means this is my system where I am having spring and damper, and this is my mass. So my natural frequency is fixed now. If I will assume that zeta is 0.1 for this damper, and now I am giving different frequency excitation, means omega 1, omega 2, omega 3, omega 4. So every time my r value will change, my r value will be omega 1 by omega, then r will be omega 2 by omega natural. So in this way I will try to see the response of my system for different value of excitation frequency, and here is the response curve. So the first curve is corresponding to the zeta 0. So zeta 0, that means it will equal to a case of undamped vibration. If I will increase the zeta value, suppose this is my zeta is equal to 0.2, this is my zeta is equal to 0.3, this is my zeta is equal to 0.4. As I will increase the zeta value, what I observed that for a particular value of zeta, the curve directly go below the 1 value. How this 1 has come here? If you will carefully see in my expression, if I will put r is equal to 0, the expression will say that for r is equal to 0, it will be equal to 1, because this is my expression, not this one. This part will come here for this graph. So when r will be 0, this term will equal to 1. So every graph will start from 1. This is one important observation which generally asked in competitive examinations. Then as the r value will increase, the response amplitude will increase. After crossing the resonating condition, which is r is equal to 1, the response amplitude will decrease, and finally it will go to the close to the 0 value. But as I am increasing my zeta value, what I observed that for a particular zeta value, the curve first, amplitude first increases and then decreases. But then after beyond a certain zeta value, it directly goes below this 1 line. And how it happens, we will see both from physically and mathematically. But before that, let me show you that when I am having a zeta value 0.2 and I am putting this zeta value here 0.2, and then I am varying my r value, what I observe that this curve go like this, then the maximum value and again drop. But the maximum value here is not corresponding to r is equal to 1. Instead of that, the maximum value is somewhat before r is equal to 1. What does it indicate? It indicates that if I will see this plot, it is like a resonating condition, but my resonating condition is coming before the natural frequency. So suppose my natural frequency is 10 Hz for this system. I am having certain damping which defined by 0.2, and now I am changing my excitation frequency. So my excitation frequency, the maximum amplitude will not be at 10 Hz. Before the 10 Hz, maybe at 9.5 or 9.8, I am having my excitation value, my response value maximum. So this is second observation which we get from this expression. So in case of damped vibration, your natural frequency, your maximum response is not at the natural frequency. Instead of that, we have already seen the damped natural frequency. That damped natural frequency is what? 1 minus zeta square omega n. So when for a particular zeta value, you will get the maximum response at your damped natural frequency. So please remember it. Now how you can get this zeta value which will having a curve which is directly going below the line 1. So what you can do, you know that if you are interested to find the maximum response value for a particular r, for what r you are getting the maximum response. So what you will do, you have this m expression which is your, this is your m expression. So you will differentiate your m expression with respect to r. When I will differentiate this term, finally I will get an expression which shows that my r will be 1 minus 2 zeta square. No need to remember this derivation, it's simple, you can recall or you can do by yourself. What is important here? Important that when you will differentiate this m term, you are getting a relation between the r and the zeta. That indicates that for this particular r value, this is my r star. Your amplitude will be maximum. And what would be the magnitude value of that amplitude? So what I will do, I will put this r star value into my expression. This is my expression. So when I will put this r is equal to 1 minus 2 zeta square, my amplitude of the m will be maximum, and the maximum m is what? This is the expression for maximum m. But you can see here that this expression is valid only when zeta is less than 1 by root 2. If my zeta will cross this 1 by root 2 value, this expression will become imaginary. So this is not valid here. That means whatever zeta value you are considering to see this kind of behavior, this is valid only when zeta is less than 1 by root 2. That means when the zeta value cross this value, your curve will not follow this curve and your curve will be look like this. There are more mathematical proof for this, but at this point this is not important how we have derived this. Important thing is that what is the value and how we can interpret. So this curve basically represent that in case of this much damping, your system will not have any higher magnitude, your amplitude will decrease with increase in the excitation frequency. But for other zeta value, your amplitude will first increase, show a maximum value, and then it will decrease. So this is the plot of your magnification factor. Now let's try to understand the things physically. what is happening here? I am showing three graphs here. Suppose I am getting response of a damped system. My natural frequency, let's omega n is 5, that is equal to under root k by m. I am giving an excitation which is having a value f naught cos suppose 10t. That means my excitation frequency is having a value of 10 omega, but my natural frequency is 5, and as I said that my solution will be combination of homogeneous part and particular integral part. Homogeneous part represent the free vibration section, so this is my free vibration part and this is my particular integral part. So this is my general solution or complete solution. Now what is happening actually, this part tries to move your system in this way, and you know that this is the damped case, so with respect to time your amplitude will decrease, and if you will find the time period of this time period will tell you the damped natural frequency. On the other hand, this part will try to move your system with different frequency, and that will be defined by the excitation frequency. So this response corresponding to this term, this response corresponding to this term, but what will happen actually, both will superimpose and finally you will get this response, where what will happen till this point where I am assuming that my response will have some value, the two will superimpose and my final response will be combination of these two parts. Beyond that point, when this natural part have negligible amplitude, ultimately only this part will remain in your system, so finally you will have the total response will be in this way. So till this point where the two will exist, I call it the transient zone, but beyond that the forcing part will only exist because this natural part will die out because of the damping, and this part is known as the steady state zone, and this is the transient zone. There are more detailed topic to get the transient response and the steady state response, but for the scope of this course we are more interested in the steady state response. But you should understand that what is the transient vibration and what is the steady state vibration. Now I will close this session with very simple example, that suppose we are having a case of mass, spring and damper. I am exciting the system by 100 cos 10t. 100 is the amplitude of my force, 10 is the angular frequency. Now I know my natural frequency will be what? My natural frequency will be k by m in under root k by m will my natural frequency, and I am interested to get the response. So my response will have two part, homogeneous part and the particular integral part. But as I said here in the question, it is hard to find the steady state response. Why? Because certain period of time, after certain period of time, the homogeneous part will die out and there will be only the steady state part exist in your system. So if you are interested to get the steady state response, this is the steady state response. The formula for the steady state response is this one. That means first you have to calculate the x and then you have to calculate the phi. These are the formula for x and phi. As I said, you should remember these two formula. So this is the response. These two terms will come into your response, and finally I will get all the value by putting all the input. That my natural frequency will be under root k by m, so I will get my r will be 0.5, as well as zeta will be what? C by cc, so that is also coming out 0.05. when I will put this r and zeta value here, as well as this del static will be what? F naught by k. I know my F naught is what? F naught is 100 given, and k is what? 4000 given. So I will put this value, so I will get this del static. After putting all the value together, I am getting that my x is coming out 0.03326 meter and my phi is 3.81. So I will put this in my solution. This is my solution for steady state part. So when I will put this solution, this is my expression, where this, please remember, this is in radians. I have calculated in degree, so I converted here in radians. So this is my final response. This is steady state part, not the transient part. So if I am interested to find the amplitude after a time t, what value at 5 seconds, so I will put t5 here and I will get the x value. If I will differentiate this term, I will get velocity, as well as I can also get the acceleration. So in this session we have covered the damped part, and let me tell you, no need to mug up all these derivations. What is important is what is the variation with respect to the R value. So this plot is important. What are the interpretations for this plot are important, and then finally you have to remember these two formula to get the solution of numerical. Now in our next lecture we will cover very important topic, that is the transmissibility, and if you are applying certain force to your system, how much force will be transmitted to this ground, and that particular call is the force transmissibility. And we will also solve one numerical for a vehicle moving on uneven road. Thank you.